Right, hello. I want to talk very briefly about problems, a few problems involving altitude and declination. Um, I mean, you've got these two separate ways, two separate coordinate systems, if you like. Uh, you've got the one involves right ascension and declination, which is essentially a sort of projection of the latitude and longitude on the Earth, projected onto the celestial sphere, and that's sort of fixed for everyone. You know, everyone sees the same coordinates in that particular system. And on the other hand, you've got the azimuth system, where you've got an altitude, which is the number of degrees an object is above the horizon, which obviously will be a local coordinate system that will vary for different people on different parts of the globe. So you have the altitude, which is the number of degrees above the horizon, and then you've got the azimuth measurement, which is just the straightforward horizontal number of degrees measured horizontally, if you like. Now, these problems I'll be talking about now, they feature either the latitude or the latitude of the observer or the co-latitude. These feature quite prominently in these problems. So you can get away with just quoting the latitude and longitude to a certain extent, but I want to just try and explain a bit more about how they come about. As I say, co-latitude is 90 degrees minus the co-latitude is 90 degrees minus the latitude of the observer. So a standard way to start would be to I'll use the same paper. That's the horizon. This is the North Star. Now, what is that altitude? Well, that altitude is equal to the latitude of the observer. So, somewhere like Liverpool has a latitude of approximately 53 degrees. So that for us, that will be 53 degrees above the horizon. I might have equally have said, okay, how do you find the latitude of your own latitude? Given that you've got this great problem, you probably know about how to not mystery, but problem of how to work out longitude, particularly at sea and so on. But on the other hand, how to work out your latitude is much easier. If you're in the North Hemisphere, then the latitude is equal to the altitude of Polaris, i.e. the number of degrees above the horizon. Now, if I can make that start a new sheet. If we've got Polaris there, and that's the horizon, then the next question would be, what's the condition for a star to be circumpolar, i.e. To be in the sky all year round? Well, the stars are going to circle around Polaris like this. So, you might need to use a bit of imagination here. But that's going to be the limit, okay? That star is the limit as regards circumpolarity. Any star with a lower down is going to be cut off for part of the year, and it's not going to be in the sky all the year round. So what is the declination of this? Well, the declination is just equal to the co-latitude of the observer. I've just mentioned the co-latitude, and you can see this by virtue of the fact that if I'm here at 53 degrees, that's Polaris is at 90 degrees declination. So this declination of this star here that just about makes it to be circumpolar is going to be 90 minus 53, which equals 37. Okay, so, but, well, I should have stated also that this is the co-latitude. For someone at 53 degrees, this is the co-latitude, and that equals the declination of the star that just about makes it to be circumpolar. So in order for a star to be circumpolar, it has to have a declination greater than the co-latitude of the observer. So what I'm trying to say is that you got the calculations which involve the latitude and the co-latitude all the time, but I'm just trying to put a bit, show the picture as to why that should be. It's there's no great mystery behind it. Now just as the Polaris is offered an altitude or equal to the observer's latitude, the celestial equator will have an altitude equal to the observer's co-latitude. Now, let's see. If I was to think of a situation at the North Pole, this is at the North Pole here, the North Pole. What would happen is that the altitude of the North Star, or Polaris, would be off at 90 degrees. It would be directly overhead. And the altitude of the celestial equator would be 0 at, well, it would be on the horizon. Now, I'm cutting a few corners here, but if you can accept that, the particular time of year when the pole star is directly overhead at the North Pole, the celestial equator will be off on the horizon. I mean, there's another little thing I find in practice that confuses people a bit is that you might think, okay, that there's the sun. That you might think that the celestial equator might be off at an angle, but the point is that this is obviously not to scale. The fact is that the sun is quite a massive object, and it's 150 million kilometers away. So in effect, the Earth would just be represented by a minor speck. I mean, even that's much too large. So the effect is that any light coming from the sun detected on the Earth, essentially you consider the position of the sun from the Earth to be equal for everyone. Everyone will see the light from the sun coming in parallel to the ground, if you like, such that at the North Pole you'll see it off like that. Obviously, the equator you'll see it sort of coming in parallel, but anywhere on Earth we'll see light coming in from the sun parallel. So that is valid. There's none of this off at an angle business, because of the scale of the thing. Everyone sees light coming from the sun along parallel lines. So that is valid. Okay, to say that the celestial equator is off on the horizon. Okay, sorry about that. There's a slight diversion possibly, but I know that sometimes, quite often people are a bit confused about that. But if I come down to where I am at, I'll okay, I'm making a bit of a mess of this actually. But where I am, okay, at 53 degrees, what I'm trying to put across in this diagram is that you'll still have a right angle between the direction to the Polaris and the direction to the celestial equator. I'll probably best if I start off on a new diagram. So here's where I am at 53. Polaris will be off at 53 degrees altitude, and obviously this is not to scale, this is a bit of a, excuse the mess here, but just get the general idea. So that would be the celestial equator, and that'll be off at what did I say, 37. Okay, so just at the North Pole, you'll still have a right angle between the direction to the North Pole and the direction to the celestial equator. But if you accept that off the altitude of the North Star is 53, because this is a latitude 53, then, you know, simple basic geometry will show you that must be 37 after the celestial equator. So just to be clear about the celestial equator, what I mean by the celestial equator is the celestial equator at its maximum, because the celestial equator will go across the sky like that. I mean, twice a year the sun is actually on the celestial equator, so you can imagine that, you know, the sun does track across the sky like that. And so what I'm really after is this point here, okay, i.e. if the sun was on the celestial equator, it would be at its highest point at noon, and that's the point what I'm talking about when I say that this is I'm pointing here to the place where the celestial equator is at its highest, i.e. that's when it will have an altitude of 37 degrees. So if you can measure the altitude of the North Star, then you can work out your own latitude. Likewise, if you can measure the position of the celestial equator, or the highest point of the celestial equator, you can also measure your own latitude as well. But obviously, when you're doing this type of calculation, you're actually checking the sun. If the sun is actually on the celestial equator, then, you know, a direct observation of the sun at its highest point will tell you where the celestial equator is. You know that the celestial equator, the altitude here, the altitude of the celestial equator is equal to your own co-latitude, and therefore you can work out your own latitude on the Earth's surface. At other times, the sun is either above or below the celestial equator, so you'll need to look at the relevant charts to find out what the declination is of the sun on a particular day. So if the declination of the sun is 10 plus 10, you would do your observations and capture the altitude. Perhaps I would put it like that. Capture the you capture the altitude of the sun at its highest point. You then need to deduct 10 degrees from that altitude to get the position of the celestial equator. And once you've done that, as before, you can work out your own latitude. Might get a question saying, okay, if you're on if you're standing on the Tropic of Cancer and the sun is overhead on the Tropic of Capricorn, what is the altitude of the sun? Well, on the Tropic of Cancer, if you're standing on the Tropic of Cancer on the Earth, the altitude of the sun is 90 minus Okay, the altitude of the Sun will be your own co-latitude, and because you're on at plus 23.5 on the Tropic of Cancer, that will be the altitude of the Sun. That would be the altitude of the Sun if the Sun was on the celestial equator. Okay, because well, let me be more precise with this. If you're on the Tropic of Cancer, the altitude of the celestial equator will be given by this. So if the Sun was on the celestial equator, that would be the altitude of the Sun. But as I said, in this particular problem, the Sun is on the Tropic of Cancer, Tropic of Capricorn, so that'll be 23.5 lower. So perhaps I should just make that altitude of the Sun on the celestial equator is that here, because the Sun is over the Tropic of Capricorn, it'll be 23.5 degrees lower than that. So it'll be that, which is the altitude of the celestial equator, minus another 23.5. So that's 43, okay. So if you're standing on the Tropic of Cancer on Earth, and the Sun is over the Tropic of Capricorn, the Sun will have an altitude of 43 degrees. So I've done it in steps. I've said, okay, what is the position of the celestial equator? That's equal to your own co-latitude. And because the Sun is now over the Tropic of Capricorn, it'll be 23.5 degrees lower than this figure. So it'll be at 43. We'll just finish off by talking about how you can work out the declination of a star from its altitude. If a star has an altitude of 30 degrees, the question would be, what is the declination of that star? Now, the rule is basically, or the fundamental rule you need to take into account is that the difference in altitude, although altitude and declination are different coordinate systems, the difference between altitude will equal the difference in declination. So what I'm going to say is that if I compare the difference in these two systems between the relevant figure in the zenith overhead and the star, then they will be equal in both systems. So I mean, if this is altitude, then overhead by definition will be 90, and here's the star at 30. So that will have a difference of 60 degrees between overhead and this star. So what I'm saying is that when it comes to declination, the zenith, the declination of the stars overhead down to the declination of the star, that will also be 60 degrees. So you need to know one of these two figures in order to set up an equation. And what you know is that this is the rule, is that the declination of the stars overhead will be the same as your own latitude. Okay, so I've said before that I'm at 53. I'm at 53 latitude, so the declination of the stars overhead will be plus 53. So that's it basically. The declination, the altitude is 30, the declination equals 53, which is the declination of the stars overhead, minus 60, because the difference in declination is equal to the difference in altitude. So that goes down to minus 7, okay? So, okay, I'm difficulty fitting it all on one go, but yeah, the star that I see at an altitude of 30 degrees will have a declination of minus 7. The important point being that although these two systems, the altitude system and the declination system, although they are two different systems, the actual difference between two measurements will be identical. Right, well, thank you very much if you're still with me, and see you again maybe.